Okay, so yeah, good afternoon, everyone. This session is being recorded from now on. Thank you very much for joining us today. This is week 8, and we are about to discuss the tutorial 3 for electron not power systems, sorry, power electronics. So as you know that we have 4 tutorial, and this is the third one. And we have 3 labs, and you already completed 2 labs successfully. One more lab to go, which will be next week. And this is our third tutorial, and after that on week 10 we are going to have our tutorial number 4. So that will be all the tutorials that we have in this unit, 4 tutorials and 3 labs. So hopefully all of you are doing great. Maybe power electronics, some calculations are creating some trouble for you because some calculations require integration. It might be a bit difficult for some of you, but most of you, I guess, are very comfortable with the mathematical ideas, and you guys are quite smart to handle that. So let's jump into our today's lesson. It's about DC to AC, so inverters that I think Mr. Lawrence has been teaching you for week 7 and week 8 this week. So all of you are familiar with the theoretical part, if I'm not mistaken. So are you done yet? Like all the chapter 4, if I'm yeah, chapter 4. Are you done with DC to AC converters? Did Mr. Lawrence finish the topic? Yep. Okay, that's good then. So let me share my screen with you. This is my screen 1. Okay, so my screen is being shared. What is that? This is my vegetable that I am purchasing. Okay, so not that. I want to bring that. Okay. So these are the chapter 4s of inverters, and these are our tutorials for inverters. I think better I open it in Foxit Reader to for the teaching purpose. I don't like Adobe. Adobe is a bit troublesome. Not troublesome. It's not very easy to draw around. It's a bit heavy. So let's use my Foxit Reader. I like Foxit. Where is chapter 4? This is chapter 4. Also open with Foxit Reader. Okay. So look at our first question here. It is saying that Rashid example, that is it's taken from the Harun Rashid book. A single phase half bridge inverter has a resistive load 2.4 ohms and a DC input voltage 48 volt. So determine the RMS output voltage and RMS voltage at the fundamental frequency. So few things you have to understand about this question is what is this DC input voltage? Is that the total voltage or the half voltage? Then RMS voltage of the output, that is one thing, and RMS voltage of the fundamental frequency, because we know that when we are using power electronic circuits and we are converting from either DC to AC, there will be different frequencies involved because we are converting from DC to AC. So in AC signal, we know that there is a fundamental frequency, but since our output is not going to be pure sinusoidal, that means there is going to be one fundamental frequency incorporated with multiple other frequencies so that our final output signal going to be looks a bit distorted. It can be rectangular signal, it can be some other shapes, but it's not going to be purely sinusoidal unless we do some further steps and modifications later. We can produce pure sinusoidal, adding some more power electronics devices. But here, this is we are talking about a pure like generic inverter. So our output, normal output here is not going to be pure sinusoidal. So just before discussing this solution, let me highlight your theoretical idea again. How does the half bridge inverter works? You know that there is a voltage source. Actually, total is going to be the VD input, but for AC conversion, we are going to divide the total voltage into two sources, VD by 2 and VD by 2. And there is going to be two switches, T1 and T2, and connected with diode D1 and D2. So this switches is actually the controller of the diode or the line, like which way the circuit is going to flow. Now you think that this is the voltage source, positive here, positive here, and negative here, and this is our load. So load is sort of like in the middle. So let me highlight the load. So this is my load actually. So you can see when these both of the switches are open, that means switches are off. This positive here, so the diode is going to be reverse biased, and the positive is here as well, and so this diode is going to be also reverse biased. So when both of them are open, or you can see T1 and T2 is off, then none of them are going to conduct the electricity. So yeah, then when you're going to turn the T1 is on, then this cycle will be continue and the current will pass from this direction to that direction. And if you close the T2, okay, then this side is positive, so current will pass from this direction to the other direction and go like that. So when you are open T1 and T1 and T2 individually in a different time, one time the current is passing through this way, that means from left to right, and the other time it will go from right to left. So if you consider this side is positive, that means when you have the current from the first source, then this is going to be considered as a positive current, and for this part this is going to be considered as a negative current. And this voltage is obviously going to be positive, Vd by 2, since we are considering this side as a positive. But for this voltage, we are considering that side positive. And for voltage source, this point is positive. That's why they are opposite to each other. If you just apply normal Kirchhoff's law, you'll find out that this voltage across the load will be turned into a negative voltage. So when we are opening T1 and T2 at different times, the voltage will be positive Vd by 2 and negative Vd by 2, and it will keep on alternating like that. So when T1 is on, positive Vd by 2, and when T2 is on, negative Vd by 2. So it will keep on going on like that. Okay, so just as a normal curiosity, what will happen if I on this T1 and T2 at the same time? What will happen? Who can answer me? What will happen if I open T1 and T2 at the same time? Short circuit? Are you sure, Clement, why there is going to be a short circuit? At which point is going to be a short circuit? I just opened it. It's not never going to be a short circuit. It's just closing the path, right? That diodes are going to definitely going to get short, but there is going to be a voltage across here, voltage across there. So the circuit is never going to be a short circuit. We call a circuit is a short circuit when the voltage positive and negative got connected. Then this is a short circuit. Chain is trying to no voltage drop across the load. Yeah, sort of like you are correct. No voltage drop across the load. Actually, what will happen is this positive voltage will cancel out the negative voltage because theoretically both of them are exactly equal. So this side is going to be positive Vd by 2 and that side is going to be negative Vd by 2. So they are going to be canceled out each other. So there will be no voltage across the load and so no current will be flow. The voltage source will be open as it is, but there will be no current flow through this because there will be no potential difference. Okay, so it's like that when you are turning this close down these two switch or the turning the T1 and T2 on, then the current flow here is going to be 0. So here, so that is our normal operation. T1 is on and T2 is on. Then the voltage across the load is going to be positive Vd by 2 and negative Vd by 2, and it is continuously going on like that. So this is our output voltage. So this is sort of like our output voltage. As I told you at the beginning, this is a very generic DC to AC converter. So we cannot expect a sinusoidal voltage here. So you can see this is a AC. This is definitely a alternating current, but this is not a pure sinusoidal alternating current. There are positive current and negative current. So definitely it's AC current. No issue about it, but it's not a pure sinusoidal. Since it's not a pure sinusoidal, but it's a periodic signal, that means it has a fundamental frequency. And there are other frequencies which we call as harmonics. So that's how our voltage at fundamental frequency will happen. Now, what about the RMS voltage? RMS voltage, to find out the voltage for a complete cycle here. RMS, you're already familiar with the term root mean square. So first you have to square it, then mean it, then root it. So square means what is the voltage on the positive side here and the voltage here. So the total voltage here is the voltage. That means you have to integrate it from 0 to 1 by Ts 0 to Ts by 2. Ts is the time signal for the whole period. So this is Ts by 2 in the middle, and this is Ts by 2 to complete T. So if you integrate it, integrate means is area under the curve, right? So area under the curve for a rectangular signal is very simple. You just multiply the height multiplied by the distance. So height here is Vd by 2 and distance is Ts by 2. But since it's a RMS value, so you have to square it. So we are squaring the Vd by 2 square times Ts by 2. So this part only is the voltage value here, average voltage here. Then here is going to be negative Vd by 2 square times the time Ts by 2 again. So this is Ts by 2 to complete T, which is Ts by 2. So if you integrate that part, the area under the curve is going to be minus Vd by 2 whole square Ts by 2. So if you did the square, so this is the square part divided by the whole Ts. This is the mean part. That means you are averaging it. For the total time divided by the time is the mean. Now you're taking the root. So this is the root. So RMS value equation is like that. Now you sort it out. The Ts and Ts is going to get cancelled. 2 is going to get a 4. So finally you're going to get is Vd by 2. So if you apply this 48 volt, the output RMS voltage is going to be 24 volt. Okay. That's interesting because the Vd by 2 means positive 24 on the top and negative 24 on the top, so at the bottom. So peak to peak voltage, peak to peak means from here to here is going to be 48, but the RMS voltage is going to be 24. Then peak to peak fundamental. Okay, fundamental voltage means what is going to be the sinusoidal component within that rectangular curve. It's a rectangular curve, but every DC signal is a composition of one fundamental frequency and it's multiple harmonics, maybe third order, fourth order, seventh order. It's actually when you create a DC signal like that, there are almost like infinite amount of harmonics involved within that signal. So the fundamental frequency we consider is sine theta. So this part we assume that the peak is going to be here, Vd by 2. So Vd by 2 sine theta, d theta. So we have to integrate it from 0 to half. So since it's a full complete cycle, we have to integrate it in two parts. First, we have to go from 0 to half cycle. Half cycle means 0 to pi. Full cycles, we already know 360 degree. Full cycle of a sinusoidal means 360. So half cycle means 180 degree. If you consider it in radian, we consider it 0 to pi, and then pi to 2 pi. That means 180 degree to 360 degree. So this part, the peak is going to be Vd by 2 multiplied by sinusoidal component sine theta. That part is going to be negative Vd by 2 multiplied by the sinusoidal component sine theta d theta. So we just have to integrate it. Then this is we are integrating it for the whole cycle, and since we have to find the average value or the RMS value, so you have to divide it by the pi. Okay, so because 0 to pi, we are integrating it for the whole cycle. Then if you just take the root of it, then it's going to be 2 Vd by pi. So this is the average value. And if you take the RMS, you just have to find the RMS of that. Applying the voltage, what is the voltage of Vd? 48 volt. So RMS of the fundamental, if you apply the Vd 48 in the equation, it is going to be turned into 21.6 volt. Yep. So peak current in the switch. So peak current of the switch means here. Where is the switch? How much is going to be the current on the switch? The current on the switch. Okay, oh, sorry. The current on the switch is exactly the current flowing from the source through the load because there is no other component. So whatever the voltage is here is coming through the load is exactly the current through the switch. So current through the switch is VD by 2 divided by R. So maximum load current is going to be 24 volt, which is the RMS value of the output cycle divided by 2.4. 2.4 is the resistor given. So there is no inductor, no inductor. So it's a purely resistive load. So the current going through the load for each cycle is 10 ampere. Okay. And so the current through the switch is also going to be 10 ampere. So that's how this whole inverter system for this particular case operating. So we take a DC input, but the output side we are generating a AC circuit, but it's not a pure sinusoidal AC. So that's the working principle of a normal, very generic half bridge inverter circuit. Okay. So are you fine? Could you understand it? The explanation? Okay, that's good then. Let's move forward to our question number 2. Okay. A single phase full bridge inverter. So using a square wave modulation. Okay, a square wave modulation is this type of waves. Has a DC input voltage 220 volt. So input voltage of VD is 220 volt. Determine the RMS of the output voltage and RMS at the fundamental frequency, just like we did before. And the total harmonic distortion means THD. Total harmonic distortion means the voltage from the harmonics divided by the voltage from the fundamental is the THD. What is the peak inverse voltage of the switches and the diode? So how much inverse voltage you have to apply to the diode? So this is a full bridge. So this circuit doesn't belong here. This circuit belongs to this one. So ignore this. This is not the circuit for this problem. This circuit is actually this one. It's a full bridge. So full bridge, you know the configuration of the switches. You have to be very careful about it. This is T1 and T2 is here. Sometimes the student make mistake is like that. They put T1 here, T2 here, T3 here, T4 here, but it's not like that. So always remember T1 and T2 are always be put in diagonally in full bridge. So T1 is here, T2 is here, T3 here, and T4 here. So it's like going to diagonal, going down, going up, and come back to down again. Another diagonal. Okay, so it's like a bit confusing why we did it like that, because we did it like that to make sure our remembering the situation is easy. Since we are planning to have a full bridge, that means on the output side we want to have the whole VD at the output. Because of that, if we put T2 here, then to have the VD we have to say that T1 and T4 is open at the same time, and T3 and T2 is open at the same time. So that will be a bit more complicated to remember, rather than we are saying now is T1 and T2 is open at the same time, and T2, T3 and T4 is opening at a different time. That is easier to remember. That's why we are positioning the switches like that, which is seems difficult at the beginning, but it is actually easy to remember later which switches are opening at the same time. So that's why we are putting T1 and T2 here diagonally. So T1 and T2 is going to operate at the same time. The other time, the T3 and T4 is going to operating. So when T1 and T2 is operating, you know the VA, this is the position of VA, and this is the position of the VB, which is the voltage at the other side of the output of the load. So this is the load. The output of the load is going to be VAB, which is VA minus VB. Okay, so this is your 0 point. So VA 0 means the voltage considering this point to that point, and VB 0 is voltage considering to this point to that point. Okay. So then you subtract it, it's going to be your VAB. Okay. So the RMS output voltage, okay, let me look at the circuit here given. So this is your normal operating situation when T1 and T2 is on. the output is going to be the positive. When T3 and T4 is gone, the output is going to be negative. But the difference between half bridge and full bridge is, in full bridge, the magnitude is not going to be VD by 2. The magnitude is going to be VD. That means the full VD is going to get conducted. The full voltage you can get at the output side. So that means you're using 220 in this particular problem. 220 volt. Okay, so the voltage at here output is going to be 220, but forget that notation. This notation is wrong. It should be T1 and T2, and this is T3 and T4. This one is correct. So this is the exact notation that we have to use. Now look at the solution. Solution is very straightforward. So RMS value of the fundamental. I think where is that? RMS value of the fundamentals is given here. Okay, so this is the theory, but you can try it by yourself as well. So VD, just like the formula we did here, instead of VD by 2, it's going to be VD square. Okay, that is the only difference is going to be here in the formula. So if you apply that, finally RMS, you are going to come up with the 4 VD over root 2 pi. Okay, then you put the 220 volt will turn into 198. So RMS value of the fundamental is going to be 198 volt. Okay, so I'm repeat again how you're going to do it. Exactly just like this. The fundamental frequency here, you multiply it by sine theta. Only instead of VD by 2, it's going to be VD, because on the output side you are not getting VD by 2 anymore. The output side you are getting the positive VD and negative VD. So you apply VD here and VD here. Sine theta will remain exactly like sine theta. So integration is also going to be remaining like exactly 0 to pi and pi to 2 pi. Then you do the integration and you can come up with the same formula here, exactly like that. So yep, so this is the RMS from the fundamental. RMS from the harmonics, that's a tricky. We can calculate it in multiple ways, but one of the easy way to find it, because there are 3 components on our output side. One is the output of the RMS, which is 220. Okay, one of the RMS of the fundamental, 198. So there are 3 components. One is the RMS of the output, and in the output we know that it is a composition of fundamental and harmonics. So we consider it as 2 package. One package is fundamental package and one package is the harmonic package. So if you take the square root, this is just like the Pythagoras theorem. Okay, so this our RMS value output, this is our hypotenuse. Okay, and RMS value of the fundamental is going to be one of the side. So okay, let me draw the triangle, that will be easier. So yeah, right angle triangle. So not that big. Harmonics are always small. So like that. Okay, so the hypotenuse is going to be your RMS of the output. Okay, this is going to be the RMS of the fundamental. This is going to be your RMS of the harmonics. So now you apply the Pythagoras theorem, you can find out the RMS value of the harmonics. Okay, so total harmonic distortion is the RMS value of the harmonics, which is 95.81, divided by the RMS value of the fundamentals, which is 198. So which is almost like 43.55%. So it's quite high, because in total harmonic distortion, a significant amount of voltage is belongs to the harmonics for this particular case. It's kind of obvious, because our output signal is also a square wave. It's not pure sinusoidal. That means a big portion of the voltage will be not non-sinusoidal. It belongs to the harmonics of the system. So it's obvious that a huge amount of portion is a part of the distortion. So the quality of the power by these basic systems are not very good. The higher the THD is, the loss of the harmonics is high, because when we convert from DC to AC, our AC component, like the AC devices, they are supposed to operate at a fundamental frequency like our ceiling fan or some other devices which are designed to operate at pure AC, not for harmonics based AC. So when there are multiple components coming, they are going to create disturbance within the magnetic field of the components. If you operate a motor, if you operate, say, your blender, washing machine, these harmonics are going to create a big trouble for the this inside the motor magnetic field, and it is going to reduce the lifespan of your electrical motors. That's why in our normal house we never supply this power electronics based inverter based thing. Okay, what we supply in the household is pure AC produced in the electrical power system field. What we produce, we supply directly to the houses. These inverters are good for other appliances where a small voltage DC to you have to convert it to a small voltage AC. Just like when you're producing a huge amount of solar power in a solar field, you're producing a DC voltage. And but in our household, we have air con and other motors and everything, which are the pure AC devices. So that's why from the solar field, we have to convert it from DC to AC. Then we have to supply to our household, or we have to connect it to the main grid. So that is the place the inverter will come into function. And since you see that the inverters coming with, it's not pure sinusoidal, it has many harmonics. That's why we have to design another multi special circuit here to filter out the harmonics. And it's actually band pass filter. Sometimes we use low pass depending on what kind of filter we are going to use. Definitely we have to put a filter here. Okay, then we have to pass the signal through it so that majority of the harmonics are going to get cut down. Only a fundamental frequency is going to get passed through the filter, and at the output we can get almost like pure sinusoidal. So other circuits are needed, but we are not considering for our calculation for so far. We are happy with our distorted signal. Okay, but this power quality is quite poor. 43% is a distortion. Okay, so is that okay for all of you? Could I get it? Roughly? How come you got roughly? Should be nicely. Okay, assuming roughly you got it. What about others? All of you guys are fine, or any part you couldn't understand? Chai? All good? Okay, Chai got it. I'm assuming rest of you are okay. Most of the time you don't reply, so I don't know if you have any problem or not. Let's get back to the tutorial then. Okay. Number three. Number three is a three-phase now. From the single phase, we are going to convert into three-phase. What is number three is saying? A three-phase inverter employing a 180-degree conduction has a Y-connected resistive load 5 ohm. The inverter frequency is 499 Hertz and the DC input voltage is 220 volts. So VD is 220. As usual, we divide it into two sources. So 110 and 110 here. Since it's a three-phase system, so we are going to use 6 switch. Again, remember T1 and T2 on the other corner. T3 and T4 is here. T5 and T6 also going to be diagonally here. Okay. So how to remember it? So always remember this way. These are all odd on the top. 1, 3, 5. Then come back to here is the problem. Should is not 2, 4, 6. It's 2, 6, 4. So I always remember top one is a odd number. Bottom one is going to be always even number. Okay. And 1 is here in the corner definitely, and 2 will be the other corner. So only part I have to remember is 4 and switch is not in sequence. So it's going to be swapped. 4 instead of here, 4 is here. Okay. Another way of remember it is 1, 3, 5, all the odd numbers here, and the bottom number is the odd number plus 3. So 1 plus 3 is a 4, 3 plus 3 is a 6. 5 plus 3 should be 8, but there is no 8, so only thing remaining is 2, so it's going to be 2. So 5 minus 3 is 2. So it's a plus minus 5. So 1 plus minus 5, 3 plus minus 5, and sorry, 1 plus minus 3, 3 plus minus 3, 5 plus minus 3. So that's how it's easy to remember. So again, it's a 180-degree conduction. 180-degree conduction means that every switch is going to be turned on for 180 degree, and then it will be turned off for I'm sleepy. And every switch is going to turn off for another 180 degree. The full cycle is 360, so every switch is going to be open for half cycle. So if I refer back to the full bridge inverter, where is full bridge inverter? Huh. Is that one? Yeah, this is the 180 conduction. So this is a full bridge inverter. So you can see that 1, 2, 3 is operating at the same time. Then 1 will turn off. Then 2, 3, 4 is operating. Okay. Then 2 will be turned off. Then 3, 4, 5 is operating. Then 3 will be turned off. 4, 5, 6 is operating. So every 60 degree, there are 3 switches are operating at the same time. Okay. So now look at it. The switch 1 is operating for 380 degree, and this signal is going to keep on rotating. So 561, 612, 123. Switch 1 is operating. Okay, 6 is operating. 6 will another 6 will come here later. So from here you can see 2 is operating from here. So 612, 123, 234. So 2 is operating for this 3 cycle. Then 2 is not available anymore. What about the 3? 3 is started here. So 3 is started here. 3 is operating for 1, 2, 3, 2, 3, 4, and 3, 4, 5. So switch number 3 is available for another 180 degree. So this particular sequence will keep on rotating, and this kind of conduction, we call it, it's a 180 degree conduction. So what is going to happen in 180 80 degree? Let's take that 360 degrees full cycle. So 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6, 5, 6, 1, and 6, 1, 2. So this is all together 360 degree. And remember that these whole cycle keep on continuing. Now, if you refer back to the circuit, here, okay, this is our point A, this is point B, and this is point C. So from A, you're taking output, from B, you're taking output, from C, you're taking another output. So these are your 3 lines. Since we are designing a 3-phase output system, so this is going to be 1 phase, another phase, and the 3rd phase. There is going to be a neutral point, which is not shown here. So since they said it's a Y connected, so there is going to be a neutral point here. So I'm drawing it here. This is my neutral point, and the load will be in between your line to the neutral. So there is a load here. Okay, let me draw it by pencil. Zigzag. No. So this is my not a beautiful resistor. It's always difficult just to draw with the mouse. That's why we need the teaching pad, Surface Pro. Yeah, so similarly, there is a load here is connected, and this is the single phase. So every single phase, and this is a Y connected system. So you already know about the phases in the Y connected. So this is a 3-phase, and the neutral will become here. So look at the output signal now. So 1, 2, 3 is on. So what about the circuit A for the first part? So here, the port A will be open when 1 is open and 4 is open. B will be operating when 3 is open. Sorry, not open, close. 1 is on and 4 is on. Then B will be operating when 3 is on and 6 is on. And C is going to be operated when 5 is on and 2 is on. So now look at only from the perspective of A. Okay, so when 1 is on and 4 is on, then there will be voltage at the output side here. So look at it. 1, 2, 3. 1 is on, so there will be voltage here. 2, 3, 4 here. So 4 is open, so there will be voltage here. Okay, 4 is on, voltage here. 4 is on, voltage here. Okay, Then again, when the no more 4, 1 is back. So 1 is voltage is here, voltage is here, voltage is here, positive voltage. So always another thing you have to remember, this top side, the T1, T3, T5 is going to induce the positive VT by 2, and 4, 6, and 2, that means the bottom side is going to induce the negative VT by 2, just like the half bridge inverter we discussed at the beginning. So top switch is going to be positive voltage, bottom switch is going to induce the negative voltage. So you can see when the 4 is on, the voltage is negative. What about the B? B is operating when 3 and 4, 3 and 6 is on. So first part 3 is on. So 3 is positive, 3 is on. Yes, positive volt, positive volt. No more 6. Here the 6 is starting here. So 6 is like that. Okay, that's nice. Very beautiful signal. What about the C? C will be operating when 5 and 2 is on. Here 2 is on, 2 is on, but 2 is on the downside, so it's a negative voltage. 5 is on, 5 is will remain on for 3 cycle. So 3 cycle, 5 is on. Okay, and then again 2 is on. So you can see some wonderful features here. None of these signal like 1 and 4 is not operating at the same time, 3 and 4 never operating at the same time, and 5 and 2 is never operating at the same time. So they are operating alone, either this or that. So these are the signal for VA, VB, and VC compared to the O, which is your neutral point. Where is my neutral point? My neutral point is here. So neutral point is Mr. O, big O. Okay. So yep. So this is our signal to A to O, A to 0 or A to neutral. Okay. Now you find out what about your A to N. Find out the voltage between A to N. Okay. Where is my N? Okay. So VAN, that means from A to neutral, is going to be VAO minus VNO. Okay, there will be another NO component. What is the voltage at the neutral point to O? Where is the neutral point in O? Let me write the NO. Okay, this is not actually neutral point. This is the N. This is my neutral point N. Okay, this is not the O. Where is my O? Oh, they didn't denote the O here. So just assume that this is the AO, BO, and CO. So what about the, if this is a balanced system means the loads are balanced and the voltage produced and ABC is the similar voltage of the similar pattern, then we call it, it's a balanced system. If it is a an AN plus BN plus CN is going to be always 0. So if you put these equations back here, VNO or neutral to the every phase at the beginning of the phase, it's going to be VAO. If you just put it here, NO is going to get cancelled. Not cancelled, it's going to get add up by 3. So VNO, 3 VNO is going to be 3 VNO divided by 3. So VAO plus VBO plus VCO divided by 3 is going to be VNO. So now what about VAN? VA to N is going to be VAO minus VNO, which is this particular voltage you have to subtract to find the voltage between phase and neutral. So what is the voltage between this phase and neutral is VAO minus VNO. So let's do it. Where is the neutral voltage? Where is my circuit? So yeah, so VNO, you can see the VNO is VAN plus VBO plus VCO divided by 3. And since our since our voltage is VD by 2 for one particular cycle, then you divide it by 3, it's going to be VD by 6. So VNO is going to be VD by 6 here. So it's going to be a pure repeating cycle. Okay, and is going to be VD by 6. Now VAN is going to be VAO minus VNO. So you subtract it, this one minus this one. So this part is positive. Okay, this part is positive VD by 2 minus VD by 6. VD by 2 minus VD by 6 is going to be VD by 3. So the magnitude is reduced. This is already, this is a negative, and this is also negative. So the value is going to get VD by 2 minus more this, so it's going to be also get reduced, minus VD by 3. So this is positive here, this is negative here, so negative minus positive is another negative, so negative negative is going to get increased. Then this one is negative, this is also negative, so negative minus negative minus minus will become positive, so value is going to get reduced here. So the maximum peak value you can achieve is negative 2 VD by 3. Okay, and this signal will be keep on repeating itself for VAN. This is particularly important to remember is VAN. Then what about VAB? VAB, we can write the VAB is VAO minus VBO. That means connect the, where is that? A and B here directly from a load, directly A to B, there is a load here instead of a neutral point. Then we can call it is the VAB. VAB is the VAO minus VBO. What is that? Yeah, VAO minus VBO. So if you subtract the VAO minus VBO, so this one minus this one, so you can see this part is positive, this VBO is positive, positive minus positive is a neutral, 0. This is negative, negative minus positive is more negative. So this is negative VD by 2 minus positive VD by 2 minus another VD by 2. So VD by 2 is a VD, which is the full voltage you are going to get at the output side. Okay. So this is going to be full VD again. You can say this is a negative, negative minus positive is another full cycle. Then this is a negative, and this is also negative, negative, negative will become 0. Then this is turning into positive, positive minus negative is another double positive. So double positive is VD. So you can think about it as this is the full bridge output. If you consider it's a Y connected, but it's a line to line voltage. Line to line voltage is VAB. Line to line voltage is a full voltage you are going to get at the output side, peak to peak. But if you are going to take only the phase voltage, which is A to N, the peak to peak voltage is going to be 2 VD by 3 to minus 2 VD by 3. So which is, if you add them together, is 4 VD by 3. Okay, peak to peak voltage for phase voltage is 4 VD by 3, but peak to peak voltage for VAB is positive VD minus VD is going to be 2 VD. Okay, so these are the two important findings we have to remember from here. Okay, then, so let's the same same diagram is presented here as well. So yeah, so the output frequency we have to find out for every phases, right? What is the question asked? What is the switching frequency of the switches? It's not important, it's a 180 degree. So the fundamental frequency and the switching frequencies is going to be same since it's a 180 degree conduction. Determine the fundamental component of the phase voltage and the current, the peak current through the switches and the peak inverse voltage. Okay, so we have to find out the fundamental component of the phase voltage. So our main concern is VAN here. So think about the VAN. Okay, you can see this is if you look at from this perspective, from this point and onwards, this is not a repeating signal from this perspective, because it's going to be like 1, 2, 3, 4, 5. Then this is going to be already your 360. So if you consider this is your 0 point, it's not going to be a repeating signal. Okay, but if you consider this, where is that? Yeah, if you consider the 0 point to be here, then you can see this is a repeating signal. This is negative half, this is positive half, again going down, going up, again negative, negative. So this part and this part you can see is almost identical. So instead of considering this point is 0, if you consider this point is your 0, then your signal is going to be a repeating sinusoidal, not sinusoidal, repeating signal, oscillating signal. But if you consider your 0 point is here, just like normally we do, this is not a repeating signal at all. Okay, because in repeating signal, it should be repeated after a certain time. But you can see there is no repetition here if you consider this is a 0 point. So let's find the fundamental component here first, then I will tell you what is going to do here when the 0 point is considered somewhere else. So first look at it, this signal. As usual, before we have to integrate it for the full cycle. So this is a positive VD by 3. Okay, so VD by 3, this is negative VD by 3, this is 2 VD by 3. So VD by 3 times sine theta, then negative VD by 3 times sine theta. We take the VD by 3 on the output side. since VD by 3 is multiplied with all the components, so we can easily take it out. So this is positive, this is negative sine theta, this is going to be negative 2 sine theta because this is 2 VD by 3. Since we take the VD by 3 on the output, there will be 2 on for this particular section. Then this one is again negative VD by 3 means negative sine theta. Then this is going to be positive sine theta. This is going to be 2 times sine theta. Okay. And you look at the sinusoidal part, this is 60 degrees, so 0 to pi by 3, then pi by 3 to 2 pi by 3 means 120 degree, then 120 to 180, 180 to 240, 240 to 300, and 300 to 360. So this is the complete integration part for this particular cycle. Then you divide it by 1 by pi, so since we have to find the average, right? Okay. So now you think, look at this particular equation. This sine theta 0 to pi by 3 and pi to 4 pi by 3. So since we know that the positive quadrant and the negative quadrant for the sine is all positive, so this signal and this particular signal is going to be exactly the same signal. Then this signal and this signal is going to be also the same signal. This signal and the other signal is going to be also the same signal. So we can add them together. 2 times sine theta, 2 sine theta d theta, and minus 2, and this one will turn into minus. So minus minus 2 is going to be 4. Or the other round, if you do not like to think about the trigonometric quadrant, then I suggest you just do the integration here. That's it. Every single term you do the integration and you can still find out the same output at the end. Okay. But if you want to make your expression smaller, then you can think about the quadrant system and convert it to same component. This one is going to be same like this one is this, and this one is this. But if it is too hard, you don't have to convert it. You just do the integration directly here because all the components are a very simple component. Integration of sine theta, we know that it's a cos theta. Then you apply your lower limit and upper limit. That's it. So yeah, whatever you do, whichever procedure you follow, either the direct integration or you modified it like this, and finally you do, the sine theta. If you integrate sine theta is cos theta, negative cos theta, then you apply your lower limit and upper limit. You can find out or come up with this particular value. Then cos pi by 3, that means cos 60 degree. Cos 60 degree is equal to half. 2 pi by 3 is half. 2 pi by 3 is 120 degrees, negative half. So all these values you put here. Minus half is a negative 1. 2 pi by 3 again, pi by 3 is negative half here, negative half, minus half, plus half is negative half. So all the values you put, finally you can get this final expression, which is negative VD by pi. So if you can see something that when you apply your integration nicely and properly, all the calculation will turn up to a very simple term in the end. In power electronic circuit, if you can do the integration, the final part will be always a very small term or simple term. Is never going to be a very complex or big composition of multiple terms. Is not going to be. Most of the cases, it is a very simple term in the end. But the process is a bit long, and you need to be efficient with integration, differentiation, and some part of the trigonometry. Okay, so this is part is there, minus VD by pi. Now look at the signal here. Since we already discussed here that this particular signal is not a repeating signal. If I consider that this is a 0 point here, that means this one is not pure sinusoidal. That means there is not only sine theta component. It means there are other component. Since our sinusoidal components are composition of sine theta and cos theta and tan theta, but tan theta is impossible to implement it here because tan signal is not like this. Tan signal, you remember the curve, it will go at 90 degree to infinite and negative 90 degree also infinite. So that means there is no tan involved. Only two component we can consider is the sine component and the cos component. So since it's a repeating signal and there is no infinite value here, so we have to assume that there is sine component and the cos component. So sine component we found here already. Then we apply, instead replace the sine theta, we replace with the cos theta. Rest of the things are going to be exactly the same. So now you apply cos theta, apply your upper limit, lower limit, and you can find out with this particular value. So we call it, this is your sine term and this is your cosine term of the fundamental component. Then as usual, RMS value, you take the square, then you take the root. So again, you can see after all this trouble, our final expression looks like a very cute one, very nice, and a small 2 VD by pi. So in the end, you will feel relieved that you did a wonderful job and you come up with a very nice expression in the end. So now look at it. This is the same signal as before. So this was the 0 point. Now instead of that, if we consider our 0 point is here, then we can say that this is a symmetrical signal on the right side and the left side. In that case, we do not have to consider that there is a cosine component involved, since it's a nicely repeating signal and our 0 point, based on the 0 point, then we just have to consider there is a sine component, no more cosine component. But since our 0 point is here, so our upper limit and lower limits are going to be a bit different. From this side is going to be 0 to pi by 3, then pi by 3 to 2 pi by 3, and then 2 pi by 3 to pi. So this is from our 0 to 60 degree, 120 and 80 degree. What about the back side? Back side is the other way around. It's going to be 0 to minus pi by 3, minus pi by 3 to minus 2 pi by 3, this part, and then minus pi to minus 2 pi by 3. So until this part. Okay, so we integrate for this. Okay, we are integrating this much only. Where is my command? Yeah, this part we are integrating, and this is the repeating part. Do not integrate this part. This is not part of the repeating signal. Repeating signal is this much, and this is the other side. So it's perfectly symmetrical. Since it's symmetrical, we are considering that there are only sinusoidal component here. So, but your lower limit and upper limits are going to get changed because your 0 point is somewhere in the middle. So this is going to be negative side, this is going to be the positive side. So you can see our upper limit and lower limits are got switched. Then you do the integration, and finally you can see the expression is exactly the same. This is 2 VD by pi, 2 VD by pi, and voila, so you made it. Is exactly the same. So if you can find any symmetrical point inside any output of any power electronic circuit, you can always take advantage of that, and you can make your calculation less complicated, and you can take it as an advantage if you go find any repeating portion within any power electronic circuit. So yeah, you can see we can do this integration in two ways, and both of the cases you can come up with the same result at the end. Then rest of the part is very simple. You already calculate the fundamental component RMS value. So you put the VD here and calculate the value, peak value. Then if you take the root, it's going to be RMS value. Then what is going to be the reverse? Where is the question? Reverse switch current, peak inverse voltage of the switches. Peak inverse voltage of the switches is very simple. If you look at a circuit, where is our circuit? Our circuit is here. So all the switches is here. Okay, so when one switch is off, then the maximum reverse voltage you were experiencing is 120 volt, 120 or 110. 220 is the output, so 110 you are experiencing it. Okay, when the switch is on, then you are experiencing the negative 120. So peak to peak you are experiencing is 220 volt, the full voltage you can experience per switch. If you consider it alternatingly, they are operating on the switching point. So the switching voltage is also oscillating, just like our oscillating signal on the output side. So that's why the switching voltage for is exactly like VD 220. And the switching frequency, as I told you, switching frequency and fundamental frequency are same because this is a 180 degree conduction. If it is a different conduction like 120 degree, the fundamental frequency and the switching frequencies, there will be some difference between them. That is a discussion of a different thing. Okay, so yeah, we are done for this problem. Are you guys okay? Or dead already? How many? 15. Okay, let's go to. Andy is trying to write something. Let's wait for him. In the meantime, let me grab some water. Where is my water? Ah, I forgot it. Same as Ben. Okay, yes. Andy and Ben always go together. Okay. Let's get back to our PDF file. Okay. Question number 4 is saying that the he output should not be he output. The output. Where is my T? So go back. Yeah. The output. The output voltage of the single phase full bridge inverter is controlled by a PWM pulse width modulator, PWM per half cycle. So every half cycle you are controlling the input signal. Without the PWM signal, you know, you're going to always get the full pulse. That means a positive pulse or a negative pulse. But the moment you are applying a PWM pulse is a triangular signal, just like that. Where is my PWM signal? Okay, so this is a PWM signal. There is a triangular signal, and when you're switching or your switching signal is crossing the triangular signal, you can see that your pulse is going to get modulated. You're not going to get a full DC signal, full DC signal on the negative. There is going to be pulse by pulse. The moment you are crossing the triangle, like your signal is below the triangle, it's going to be 0. The moment is above the triangle, it's going to be open. Like for this case, you can see this is your signal control signal. This is the triangular signal. Control signal is more than the triangle. This is open. Then triangular signal is more than the control signal. This is closed, or the negative, the other way around. Then again, if your control signal is more than triangular, then it's a positive pulse and it's a negative pulse. So by comparing two signals, the control signal and the triangular signal, we can generate pulses. Okay, so this is the pulse for A, this is the pulse for B, and this is the pulse for C. Nevertheless, for this particular question is very simple because they say that our pulse width modulator controlled by PWM pulse per half cycle. So only half cycle is being controlled by PWM. Determine the pulse width for the fundamental RMS component. So you have to find out the pulse width of this signal to be 70% of the DC voltage. So instead of VD, this is actually only what do you call it, 70%. So instead of get the full VD, you're going to get 0.7 VD at the output. So I think in the theory, the equation was discussed, if I'm not mistaken. Where is the equation? Pulse width modulator for 3-phase inverter should be here. No. Is single phase or 3-phase? Oh, sorry, it's a single phase. I'm showing you the 3-phase one. Where is the single phase? 3-phase inverter. Yeah, this is the single phase, you can see. Okay. So single phase, you can say this is a pulse width modulator. There are multiple pulses, but for your case, there is only one pulse here. Where is that? Equation. Sine omega t, not this. Yeah. So this is our target equation here is given. Where is that? So VD, root PD over pi. So this is for the VRMS value of a half cycle. So this is the particular signal you can look at. Another equation where sinusoidal components it's involved. Is that sine d by 2? It's not mentioned here, should be. Let me find, yeah, this is the one, yeah. So equation number 10. So for the fundamental RML voltage is this one, 2 root 2 VD by pi sine d by 2. So this is the one. This is the fundamental RMS voltage for a single phase full bridge rectifier. but they said the output is going to be 0.70, so we can make them equal. So this is the fundamental RMS voltage, which is equal to the 70% of the DC voltage. So 0.7 times D. Then you can calculate the value of the D. D is the pulse width. How much is the width of the pulse? Since it's a theta domain, this is not a time domain, this is a angular domain. So we are calculating the value in radian. Okay. You can calculate in degree as well, but just make sure you're putting the calculator into the right mode before writing the answer. Be careful about your mode of the calculator, what you are doing. Okay, and they ask you to find out the time. Is it the PWM with one pulse per cycle is a single pulse? Determine the pulse width. We already did. Okay, what they're looking for about the time. So what about the time? Time is, theta is equal to omega t. So this is the equation for angular to time domain. So time is equal to theta divided by omega. So angle we already calculated from this point to this point is the angular domain of the D. Angular domain, though D looks like is your linear length, it's actually a angular domain since your x-axis is the angle. So this is actually theta. D is equivalent to the x-axis theta, which is 1.7815 radian. So this one is going to be equal to omega t. So if you divide it by omega, omega is equal to 2 pi f. What is the frequency given? Frequency is given 400. So this one divided by 2 pi f. You can calculate the length of the pulse width modulation. How much is the length in the time domain? So just to be noted that D and T, they're almost like representing the same thing. D is the time domain of the pulse width, no, sorry, the width of the pulse PWM signal, or the width of the pulse in angular domain. And this time is the width of the pulse in the time domain. So they are representing D and T is representing two different domains, but in physical significance, they are actually uh, referring to the same signal, but the representation of the domain is a different one. Question number 5 is also similar. A single phase full bridge inverter uses a uniform multiple pulse. This was a single pulse, right? Control one pulse, so one pulse. Now there will be multiple pulse. Multiple pulse means like that. So one cycle is going to have multiple pulse. So positive pulse and negative pulse for positive cycle and negative cycle. If the output fundamental frequency is 400, again given the same 400, determine the pulse width if the RMS is 80%. So just like the previous question, the output RMS is given. So you have to find the width of the pulse. So VRMS for this particular modular multiple pulse width modulation, the equation is here. Okay. Also the equation proof is somewhere here. Yeah. So VRMS square is VD square PD by pi. So VRMS is equal to root over this. So VRMS is equal to VD multiplied by PD by pi, root over PD by pi. P is equal to the number of pulse, how many pulse you have. For this case, 1, 2, 3, 4, 4 pulse. For your case, how many pulse? 5 pulse per half cycle. So for this particular cycle, there are going to be 5 pulses. Like for this signal given here is 4 pulses on the positive cycle and 4 pulse on the negative cycle. For this question, there are 5 pulse. So the value of the P is going to be 5. VRMS is given 0.8 VD. So 0.8 VD, you put it here. VD is going to get cut down, cancelled out. Then you put the equation root over 5D over pi is equal to 0.8. So you can calculate the width of the PWM or the pulse is just rearrange it. It's very simple. Square it and then pi. So this is the angular domain for the width of the pulse. Then again, theta is equal to omega t. So this is the angular domain. So is equal to omega t. So this radian value divided by omega, you can calculate the time domain value of the width of the pulse. Just again, remember when you convert to the time domain, your angle cannot be in degree. Your angle always have to be in radian mode. Okay, degree has no relation to the time. Degree has always an angular domain. If you want to make any relation between angular domain and a physical domain, it has to be always in the mode of radian. So always be careful about the form of the calculator or the mode of the calculator, what you are putting there. So if you're radian, this is the time domain width of the pulse. This is the angular domain width of the pulse, just like that. So this is the value of the d of your pulse for angular domain. Then you convert it the value of the pulse in the time domain. Okay, so yeah, these are the tutorials belongs to the inverter. Okay, so that's all from my side. Any question from you guys? Hope you could understand it. Oh. Clement is fine. So the reason I wanted to take this tutorial face to face, because I saw that if I record the tutorial and upload it and then give you the uploaded lecture, hardly any of you saw the tutorial too. Until last week, I do not know about this week. Until last week, the total view in the YouTube, the video is only 9. Okay, so that make me a bit surprised that what happened. I uploaded the tutorial to, I think, almost like 3 weeks ago, and only 9 views. So 9 of you saw that. The rest of you, I think, is you guys are busy with other assignments. So you just kept it there and assuming that you're going to see it later. The problem will be when you are going to see it later, you are going to forget most of the theories that you're going to get covered in the class. And then you will not be able to understand some of the discussions, right? So that's why I decided to take the tutorial face to face. So this tutorial 3 will be face to face, and tutorial 4 will be also face to face. Face to face means online face to face, yeah, not the real life face to face. So yeah, that's all from my side. If everything's okay, thank you very much. If you have any question, you can ask me. Otherwise, I'll just conclude the class for today. Any question from anyone? Nope, thanks, Andy. So let's stop my sharing and what about Ben Lau? Ben is sleeping. So can we stop the recording then? Thank you very much. I'll see you guys tomorrow for EITP.